Okay, we're going to go on with solving some logarithmic equations. So first let's take a brief history back into Chapter 7 and look at this question, which would have been on your test. First thing you would realize is that you have to have bases must be alike. So you would look at this problem and say, oh, that's easy enough. I can leave this in base 3, but this 9 has to be rewritten in base 3. So 9 can be rewritten as 3 squared. The exponent x minus 1 is still the same. Now that we have our bases alike, we're really happy, because when the bases are alike, we can ignore them, because we're trying to get this side to equal this side. And we've already got the base 3 and base 3 to be alike, so now all we have to do is get the exponents to be alike. We can solve that, and we just get x equals 2. Well, remember now, we're going to start working with log problems. And that's the same question we're going to ask ourselves, because log problems are really exponents. And exponents have bases. So as long as the bases are the same, we can ignore them. So we've done a problem like this, but let's review it. Are the bases the same? Yes. Log b, log of base b, log of base b. But remember, this is John Napier's world. He was dealing with exponents, but we're smart enough that we can go backwards and we can say, oh, this must have been the problem. 3 plus really means times x gets me 12. So x was 4 in this case. Second problem. This is kind of new. We see its logarithm, so immediately we know we're dealing with exponents. So we must check the bases. Are the bases the same? Okay, up here when there's not a base written, we know it's base 10. And we know this is base 10, and now we're unhappy, because this is not written in log form. Okay, so we can work with what bases are alike. So we can work with this section right here. Let's take care of that section. All right, well, we know we have x. We know that plus really meant multiply. And then we have x minus 3. But the problem is we can't ignore the base quite yet, because not everybody is base 10. So I have this lovely little problem here, and if you notice, what we have is, well, let's get out of Napier's world. We don't want to work with logarithms. Remember, roll the log. 10 to the first power gets me that. So my base here was 10. My exponent was 1, and my answer was x times x minus 3. That was the real world problem John Napier was trying to solve. That's why he turned it into this whole logarithm mess up here. Okay, so 10 is x squared minus 3x. Keep going. Oh, we got a factor. Yes, we're back to factoring. X squared minus 3x. We'll bring the 10 over. I'll factor. So x is 5, or x can be negative 2. But we're going to check our answers. So I'm going to come back up here. Just let me erase that. Let's get that out of here. And if you put in the log of 5 plus the log of 5 minus 3, so let's get our calculator out. And let's type that into the calculator. log 5 plus log of 2. You can do 5 minus 3, and what do we get? 1. Excellent. This is an answer. Let's take negative 2 in. Log of negative 2 plus the log of, well, log of negative 2 plus the log of negative 2 minus 3, so that would have been the log of negative 5, and we get an error, a non-real answer. Yep, that's right. This is a reject answer. Didn't work. Calculator told us so. And why is that? You can't take logarithms of negative numbers. It's impossible. Try it right now. Take the log of negative 3,000, and you're going to get that same reason, same error. So why can't we have a negative as an answer? Because if we went back to our beginning, remember, a logarithm is a base, a power, and that equals an exponent. And in this case right here, we were looking for the power. We were looking for this part right here. So can something raised to an exponent ever get me negative? Can something raised to something ever get me a negative answer? No, never. Really? Watch. Because if we did, any exponential equation, see how it never goes into the negatives? Even though we raise to negative powers? See, even though we're raising to negative exponents, we never get a negative answer. So that's why this power part can never be negative. So let's write that down because that's kind of important. Okay, let's just do one more problem. All right, in this one, let's go through it. Are the bases the same? Base 10, base 10. Oh no, not again. All right, so let's get this out of Napier log world and get it back to a regular problem we can understand. Okay, if a 4 is in front of a log, we really know that was the exponent there. So that was 2 to the 4th. Plus really meant it was a minus. A multiplication. Oh, we got another number out front, so that meant it was a power exponent. And since there's not a log 10 there, darn it, I can't ignore this log 10 just yet. Oh, whew, that makes it easier. It's a roll the log again. I can bring this totally back to a real world problem. Forget Napier. I have a base of 10 with an exponent of 2, and that gets my answer as 16x squared. Oh, I can divide by 16 here. I can divide by 16 here. So 100 over 16 is x squared. And when I take the square root, I get 10 over 4, which reduces down to 5 over 2. But remember, since it was squared, I could have a plus or a minus. But hey, I know my only answer is positive 5/2, because we just learned on the slide before we have to reject all the negatives, because I can't take the log of negative 5/2. Okay, done.